Hi, my name is Sebastian. I will give you an introduction into Kubernetes. And not only into Kubernetes, but we will be talking about several topics here. We will be talking about containers. What are they? What is the differentiator between a container and a virtual machine? We will be using Docker to actually work with containers and container images. And lastly, we will be talking about Kubernetes. What problems does it solve and how does it work internally? And for me, it's not so much a thorough introduction and explanation about all these concepts, but I want to place little notes in your mental mind so you know I've heard about this topic before and it's in this area of interest or it's used for accomplishing this or that. So let's start right away. We want to answer 3 questions. First of all, what is it? Secondly, how does it work internally? And all these 2 answers combined should answer in the end, does it solve a problem for me? Do I want to employ this technique, this technology? So the complexity within this lecture or slide set will be constantly rising or fluctuating, but it will go upwards. So it's targeted at IT professionals which have not so much experience when working with containers. So let's start with by acknowledging sometimes I'm not 100% precise because I want to talk about the concept and perhaps like this 10% more precision would make it explaining very hard to follow. So sometimes I'm perhaps not 100% correct. Please bear with me here. All right, let's start with containers. And we will be talking a little bit about Docker. So you will hear that word throughout this first part of the lecture plenty of times. So according to Docker, a container is a container image is lightweight. It's standalone and it includes everything that is needed to run an application. That's very important to know. So we are not creating infrastructure for its own sake, but we want to actually run applications. Sometimes we forget that. So we take the code, we take the runtime that is needed to execute the code, and some system libraries, system tools, and we garnish this with settings everywhere along these steps. And if you look at this picture, you might wonder, what is it not a VM? We even see a Linux down there. So that's basically what we are dealing with in infrastructure since way the 90s. No, it is not. Let's go back to the 90s then. Let's see how we deployed an application back then. We bought hardware. We installed an operating system, for example, a Linux, and then we installed and configured our application and then it ran. And it ran perfectly because 90% of the time the application idled and 10% of the time it was pretty amazing fast. But it was very expensive to deploy an application like that. But from a security standpoint, sometimes it was the only way. If an application failed and, for example, a kernel panic occurred because of a faulty application, if you deployed several applications, and let's look at that, on the same hardware, on the same OS, then all the other applications will crash too. You could, if you paid attention, you could deploy several applications on the same service if you are comfortable with it, but you really had to watch out for example, not reusing existing ports. It was manageable, but it was not very great. So 10 years later, around that time, hypervisors came pretty strong into the scene because they allowed us to separate workloads by grabbing the hardware resources like CPU, memory, IOPS, and build tiny isolated sections from this hardware. This is a virtual machine. So now we can separate these workloads and we can run different applications on the same hardware without them interfering because the hypervisor isolates these from each other. The drawback is that we need to install an operating system in each of these virtual machines. So we shift this operating system up 1 step. And that is pretty costly because, like a Windows Server system, it takes quite some time to start up. It in itself requests and requires certain resources in order to function. And we need to guarantee these resources to actually run our application. And now we are duplicating this OS layer for each app. So it's pretty costly. It's not very thin, you would say in German. But at least we solved the port problem there. So around 10 years later, people started to think there must be another way, a better way, a more cost-efficient way. So Docker came up around 2013. It really gained traction. And we now took our hardware, reinstall an OS as the first layer again. And on top of that, we deploy a container runtime. And this container runtime will start the containers that we saw look like this on one of the previous slides. So our system libraries, system tools, our runtime, and our code. And the container runtime, as within the hypervisor world, separates these processes from each other, creating a room for all these containers to act in. And the container from the inside, it thinks it runs on its own hardware. It has its own host name. It has its own network stack. It has its user and file system just as a VM. But it's very, very much faster because the operating system already runs on the hardware, and this separation of processes by the container runtime is just a configuration step and then starting a process. So they are super fast. Instead of booting a Windows server and waiting for it to come up and then starting the application, we're talking about perhaps 20 to 30 seconds. This is up instantly, depending on the container size, of course, but way much faster. And resource-wise, way slimmer. All right, let's look at how we actually create such a container then. We now know the difference a little bit. First, we declare what's inside. We said in the intro, all the application needs to run is included in the container. So we need to declare what are these components exactly. What is the runtime? For example, for a server-side JavaScript application, it would be Node.js. So we need to include Node.js into this container. And when we are finished with the declaration, we build it. And then we do have a container image. And this image has a name and a tag. So we name it my web application and we tag it. So we can, for example, use version numbers to differentiate the different container images and their history, or some other structure that makes sense for me and my organization. Then we can finally run this container image, and then finally we have a container. Okay, let's dive right in. Let's create such a declaration. Let's declare what is needed to run our Node.js application. And this is done, and here the first time we hear about Docker, this is done in a Docker file. There are plenty of ways to create a container. This is just one example using Docker. So we describe here from which base image do we start. So sometimes we do not want to start from scratch, but we need for example, a Node.js runtime. So let's grab that one. It's called Node and its tag is 18-Alpine. Then we are just configuring the whole container. We are creating a working directory. We are copying the package JSON. That's the file where everything is described. Which libraries does our JavaScript application need? And then we copy the source code. We install all these Node.js libraries with the Node package manager. So these steps are pretty specific to a Node.js application. We create environment variables. We expose the port 3000 because the web server inside just listens on port 3000. And then finally, a command. We are starting a process here. And the process is the Node.js runtime. And its argument is index.js because that's the entry point of our JavaScript application. Each container needs such a process because when a container is started, it ends automatically if no process is running and keeping the container alive. So that's an important note. Please put a mental marker in your mind map. Now let's look at this package JSON in more detail. In the first part, we are dealing with file system changes perhaps. We are creating directories. npm install is basically download these libraries from the internet and place them into the file system at a specific location. There's nothing more. And then we got some configuration. And finally, I said that already, a start command. And when we are feeding this declaration to the process that creates it, that builds the container, it will go from one line to the next, and it will execute the instructions found in each line. And each line will then create a layer. A layer is the combination of file system changes from this one line, and it has a checksum. And this is repeated for all the lines in the Docker file. These layers are building up. And finally, when we are reaching the command node index.js, we've got some kind of layer cake of different file system changes. And these in combination are our container file system. It's a union file system. So if we looked from top to the bottom, we would see that a change in one of the upmost layers will override a change in the layer a little bit more to the bottom. And if we are, well, basically very honest, we would say this node 18 minus Alpine, those are multiple layers as well, and they are getting downloaded. The good thing about these layers is when I change my declaration, for example, I will change the environment variable, not all the layers need to be rebuilt, but only the ones following this change instructions, and those will form new layers. And those layers are interchangeable for all containers that I'm running on my host system. They are mounted read-only, and if I have several Node.js applications, a pretty large set of this layer cake is reused across containers. So it's very, very resource efficient. So great, now we have our container images. And as I said prior, node 18 Alpine, the base image, will be downloaded. So where does it come from? It's coming from a registry. So this is the location where container images are stored. And we can specify which registry we are dealing with by specifying its name, like its domain name, the name of the container image that we want to retrieve, and its tag. And then we pull that from the registry. And in our example, we did not specify the registry name, we omitted that. And we will, if we are building a container image with Docker, it will just assume that, you mean probably Docker Hub, my own registry. And when we are creating our own container image, perhaps from scratch, we want to share that with the world, and we push that into a registry. Again, we will specify the domain name of the registry, the container image name, and a tag. That does not necessarily mean that we are dealing with, again, with the Docker Hub. It could be a completely different container registry. And it could be a private registry. So not everyone is allowed to interact with it. I need to authenticate in order to push an image or pull. So these are examples of how you can share an image. Now let's look what happens if we actually run a container. I said the container runtime prepares the environment, and those are basically 4 steps that are taken in order to ramp up and start the process within the container. First, it will create a namespace. It's basically, I forgot to translate that. It defines what does a process see from within. For example, what user do I think I am? Am I the root user or a different user? What's my network stack? What are my process lists? Perhaps I can only see my own processes and none from the host. That's exactly what happens. And Unix time sharing, it sounds very, very important, but it's just what's my own host name from within my container. That is a different hostname than the host that is running the container. The next mechanism used are C groups. So what kind of resources is this process given? How much CPU can it consume? How much memory? How much I/O? The third step is change root. So the container file system we just created in the previous step, this layer cake, is mounted at the root file system of this container, with chroot. And finally, that's not a surprise, we will execute the start command, the process. that is running and keeping the container alive with all the environment that is inside the Docker container or the container image. And the last two steps are actually from within the image, and the other steps are instructed when creating the container, how much CPU, what's your user, and so forth. And again, this is nothing the container runtime provides to the system. The container runtime just uses the Linux kernel functionality to create the namespace, to create a C group that controls how much memory the process can use. So that brings us back to the question, is a container just a very small virtual machine? And indeed, there are similarities and there are differences. For example, I can execute or call a shell from within the container. So I can go into a container using a shell and then look at the file system if the container has a shell. Alpine Linux, for example, has a shell, and I can do that. But if I have some kind of Go code, for example, I compile that specific to the target architecture, and I can run this Go command or this executable directly on the kernel. Then I do not necessarily need an environment like Alpine Linux, and the container image is super small. But I cannot execute a shell. I cannot debug stuff very easily. I can install packages if there's a package manager in the container. I can run commands as root. I have my own process space. So those are similarities, but there are differences too. It uses the host kernel because it uses functionalities of the host kernel to create a namespace, to create a C group. So I cannot boot a different kernel or a different operating system. With virtual machines, I can have a Windows server and a Linux server and an OS2 Warp server right next to each other, and that's okay. That works perfectly fine. But here it doesn't. So it feels perhaps like a virtual machine, but if your thought process is going into this direction, it's not really correct because it's just another process on the host. So why or how would I deal with these different kind of workloads then? I will probably not only use containers in the future in my data center. I will combine both technologies. So I will still use a hypervisor to create a virtual infrastructure with virtual machines. And perhaps within these virtual machines, I can install a Windows server, and next to each other, I can install my container runtime operating system combination that will run my containers. So I will combine both on the same architecture. Now we know about containers, what they are, how can they be built, how they are declared, how we can run them in theory. But now let's dive right into and actually work with containers. And we will be using Docker as a container runtime. Docker has quite a history, and especially Docker Desktop is for me a good way to deal with containers, to learn what are containers and to initially run them, because they are not only providing you with a container runtime, but with different tools around it that makes the difficulty to start with dealing with containers pretty small. So it has a dashboard. It shows which containers are running already, and it provides you with an easy way to access a shell within a container. And it even has a Kubernetes server that you can enable with just a single click. If you're asking yourself, well, there are alternatives, for example, Podman to run containers, then you're absolutely right. There are different ways to deal with containers, running them, and working with them. And if you know about that already, you can pretty much go to sleep and wake up when we are starting with Kubernetes in the third part of this session. I'm cheating a little bit. I'm not using Docker Desktop here. Instead, I created a virtual machine with a recent Ubuntu, like a 22.04, and installed Docker in the community edition on that server. Because I want to show you something regarding network, which is not so easy on Docker Desktop, but in daily work, you can easily use Docker Desktop for your experiences and experiments. So we start with creating a container, because that's what we want to do when we are dealing with containerized applications. Normally we have an application, we need to build a container out of it. I do have some apps here. They are living in this one, and there's a sample application that I developed that wanted me to show what is the inherent IP address. Just a simple web server displaying some information. And you can already see that there is a Docker file already provided for me. So it's coming from a Git repository. You would probably pull your applications from your own private Gits or from GitHub if you trust the source. So here, let's look at the Docker file, and you will see it's very much very similar to the one that we saw in the lecture earlier. We are starting from Node Alpine. We are creating directories. We are copying files and our source code and additional, like something like a view. And then we finally install the libraries for Node.js. We define which port to use. So we provide an environment variable to the Node.js application within the container and expose this port. And finally, we run it. So there's nothing new for us to learn here. These steps, as I said before, it's like, what do we need to do to actually containerize an application that is specific to a Node.js application? You would deal very, very differently if you are packaging a Python application or a Go app. For example, you would perhaps copy the Go source code into a container, then compile it, and start a new container with the result and just copy this binary to keep the image small. So these are very advanced topics which we will not cover here, but just to mention it, there's something like intermediate containers. You need to know how to package it. Now let's assume we do not know anything and this Docker file would not be presented and created for us. So we just need to build it here, but let's assume this Docker file was missing. And all we know is it's a Node.js application, so server-side JavaScript app. We would go to a registry, for example, Docker Hub, and we would search for a suitable base image that we can use to start from, and then build our container from that starting point. So what I would do is I would just search for Node and see what's happening and what images are in the registry available to me to download and to start from. You can see there are different ones, and the top pick would be a Docker official image. Like updated 2 days ago, that looks good. Plenty of downloads and stars. So I would always look for who is building this container. What is the intention of this entity to build a container and provide it to keep it updated? Here, Docker has plenty of Node.js applications and they need them for themselves, so they will actually drive updates into the container image to be secured by themselves. Or like if a company is providing you with, for example, let's look at that. CircleCI is a verified publisher, so they have a relationship with Docker, with Mirantis, and they got this label. So there's some kind of trust between those two parties, and you need to evaluate if this kind of trust is enough for me to base my application on this container or not. Always watch out for that. That's pretty important. There are community-driven containers, and we all know how community-driven things work. They are perfectly fine until life happens and the development in this space stops or stalls and significant and critical updates are missing. You always want to make sure that this is not happening for you. So here we will be using the Node image because it's supported and it's updated recently, so we have a good feeling about that. And we can see which kind of tags we can use to start our image from, and there are so many different ones. These are very specific to which kind of image are we dealing with. Everyone has its own structure to create a semantic hierarchy of things. For example, here in Node.js, it's pretty obvious for me because I know about Node.js. The 18, 16, 14 stands for the Node.js version that is within the container. And then it's separated with dash from the underlying distribution, like the system tools. Here we are dealing with Alpine Linux, very small images. Buster would be a Debian release, or Bullseye too. So I can use the image that is most suitable for me if I need a complete Linux distribution, like a Debian. Then I would use this one. If I just need the most basic set that I can imagine to start the Node.js runtime that starts my application, then I would use an Alpine Linux because it's a way smaller container on the end. I can click on all of these links and see what's the Docker file that creates the container that I will download in my build process later on. So I can always validate what is happening here, and I can read through it and see, okay, this seems legit. So how do I define my tag? Which tag would I use? If you scroll up, it says here Docker pull node. And it just says, give me the most suitable node with the tag latest that you can find for me. Each package has one of those latest tags, but in production, I would recommend not using a latest tag. Let's imagine this. We do have our container workloads running 2 months really greatly, and then disaster strikes. We are losing our infrastructure and we need to rebuild from scratch. We haven't updated our containers for 2 months for whatever reasons, and now we are creating a new infrastructure, creating a virtual machine, installing Docker, and rebuilding our containers because we have our Docker files. And within our Docker file, a node :latest is referenced. 2 months later, we will definitely pull a very, very different base image than in the past. And how can we make sure that our application supports the new latest base image? Perhaps there is some breaking change occurring within the Docker ecosystem, not the Docker, but the Node ecosystem or Alpine Linux, and our source code is not compatible to this Node latest version any longer. So in production, use always a very specific tag. For example, you would use 18.5 minus dash Alpine 3.16. So we got Node in the version 18.5 and Alpine Linux in 3.16. It's very, very specific. I cannot recommend that enough. So it's good to see that I'm not following my own advice, and I will just reference to 18 Alpine because this is just a demo and it's really not interesting for me to be super precise, but just know about the difference and the relevance here. Great. So now we know which node image we use, and let's build this container. And this is done just by simply running docker build. And docker build just needs a build context. It needs, where's my Docker file? And we say, look in the current directory by just providing a dot. By convention, it will look for a file named Docker file, load that file and build it. Let's do it. We can see that it will run through all the steps. Each line here, it will pull the node 18 Alpine image because it does not exist in our system yet. And then it will run through all the other steps to build the container until it successfully finishes. Here we get an ID. And if we look at that ID, we can run docker image ls for list and see which kind of image, what images are now stored in our local image cache. We can see the image ID that we just got displayed over here, and we can see that node 18 minus Alpine was downloaded as well, because that's the base image. We can inspect one of those. For example, docker inspect, docker image inspect. And then how can we inspect this one? It's indicated as none and none because we did not provide a name or a tag when building it. So it's not very useful for us, but still we can use the image ID over here. And the great thing about Docker and image IDs is it can be as short as possible, but it needs to be precisely pointing to just one entity. So for example, we can just use a 7 here or 7AB because it's very different from C52. So 7AB, let's look at that. And here we can see, for example, all the layers that have been created for us and the checksums for each of them. And they are building our root file system. Docker image ls. If we log out and return to work a week later, we don't know what this image is and what's inside without a Docker file. So let's scrap that image and let's rebuild it and make it proper. We delete an image with docker image rmi remove image. And again, we will just specify some portion of the image ID that is sufficient for Docker to identify the image that we want to deal with. all the layers have been deleted now. So Docker image ls will just display node 18 Alpine. Great. Let's do it properly. Docker build. Now we will provide a name, for example, CND, because I'm very lazy, I will just abbreviate it, container network display, and we will provide a tag. So I know it's version 1.0.3. And again, we need to specify a build context. Like that. You see, it's a little bit quicker because the node 18 Alpine image has been downloaded already with this ID. Let's verify that. Docker image ls. So that's exactly the image ID, and the rest turn out pretty well. So the size is still the same, but now we do have a name and a tag for it. So again, if you return a week later, we still know that's container network display, if you remember that we abbreviated that name. Great. That's exactly what we wanted. So we have created our Docker image, and now let's start it. Docker run, and we can either specify the image ID, so 2ed, or cnd, and then we need to prefix it or provide the tag. So we need to really be precise here. And if we fire that command, we can see that our Node.js application is indeed starting up, and this output comes from the application itself. We can see that by looking at the source code from the within, this is the host name that the Node.js process sees. Where does this one come from? Unfortunately, I forgot to detach the process, so the container is running in the foreground, and I really cannot go out and kill this process without a different shell. So unfortunately, I've got another session open to this server. So let's look at the container that is currently running. Docker container ls. So Docker image, Docker container images, Docker container deals with the running containers. And we can see that indeed the image has been started. The container has an ID, 00D6. Sounds familiar? So the container ID is the host name from within the container. We got some reference already over here. We can see the image that has been loaded. We can see its uptime and its running time, and we can see a port 3000 TCP. This name has been generated by Docker if we do not specify a name for our container. Normally we do not need a name because we just treat containers as entities that we can start and kill to our likings. It's not so much like a virtual machine that we provide with a name because it will run for 5 years and we just have this cozy relationship between hardware and people. This is just some process and we do not care about names normally, but I can provide a name if I want to. Great, so we've got this container, it runs. Let's kill it because we want to get our shell back. We can stop a container by docker container stop and then provide the container ID. Or if we are a little bit impatient, we just kill the process. We remember it's just a host process, so let's kill it. It's 00D, not 6. Okay, here we go. No container is running again. Docker container ls with the --all shows us all containers, even the stop containers. Here, 13 seconds ago, we killed this one. And if we go here, over here, we got a shell back. Now let's restart this container because we just want a shell, but running the container is what we actually want to do. Docker container start, and now I can use bash completion to say, oh, Critical Williams, that was the container name. All right, let's start it. And now it's in the background. I can Docker container kill Critical Williams. I can run this container a second time. Docker run cnd. And now I say detach. So it's already going into the background and I can work on the shell and continue working on the shell. I get the container ID back. that is started. And if I do a container ls with the all flag, I can see now we got two containers. One is stopped and one is running. Clever column is the actually running one. We know now port 3000. Now let's try to reach it. Let's try some things to actually understand what is happening. So we know a process on the host is running the container, and this container has the port 3000 listening for incoming HTTP connections. We saw with Docker container logs, with Docker logs, what was it? Clever column. We can see that the container thinks its host name is this string, which is part of the container ID, right? So container ls, let's validate that. We got this one over here, and Docker inspect clever column. We can see that the actual ID is way longer. So the display already shortens it. Let's use the complete ID as a host name and try to connect to it. Curl and port 3000. Okay, my Docker host obviously doesn't know about this as a host name. It's not registered in its DNS. Let's Docker logs, clever column. Let's use this. Perhaps it's just shortened. So let's use this one and try to curl that. No, nothing either. Now we are desperate. We will use and try to use the host IP on port 3000 and see if that works. So we get the host name, the host IP address, which is this one, and curl that. Oof, missed. All right, curl 3000, and obviously, of course, the host doesn't listen on the 3000 port, so it fails already. But we know something about Docker networking. That's where it doesn't work on Docker Desktop as well as in here in this situation, because of, like in Docker Desktop, it will create a virtual machine for you which has no IP. It's a little bit more complicated, but in Docker on a server OS we can do the following. Let's inspect the running container, Docker container ls, Docker inspect 8FA, and let's grab for IP address. And here we can see there's a private internal network with this IP address, and the container is listening to that. The Docker host is able to connect to this IP address. Or is it? Yes, it is. So first time we got a response. That's great. From within the Docker host, we can reach the container. But that's not sufficient. We want to actually reach our application from outside the Docker host. So we need to publish the port. We need to provide the port forwarding from the Docker host inside the container. For that, we need to stop and start the container again. So just to see, we will stop this process. And we will restart it. Docker run, cmd, and the tag that we want to use. Here again, we will specify detach, and we will publish a port. We will say port 8080 on my host will point to port 3000 within the Docker container. And now let's try that. We know the IP address from this host is, we can use a local host. So localhost. Again, we will use port 8080 here, not 3000. And we get a response as expected. Or we can use the public IP address of the host. That's this one, I guess, if I remember correctly. And again, port 8080. Great. Let's try that from a web browser to see the actual output. So we connect to the Docker host. I already did that. And we can see here, this is the container ID. It runs container connect with display. It has this IP address in the private IP space. That's what we just learned on the command line. Nice, so now we know about how to publish a port and actually work with a web server. Let's go back and just deal with one last topic. How can we work with a repository, a registry, sorry. For that, we need to do two things. We need to authenticate to the registry, and we need to tag our image to actually say, please push this image to this registry. So this connection needs to be reflected inside a tag. So we will learn how to tag an image. We now built our CND 103. That rhymes, that's good. So let's create a tag. So let's imagine our own registry for my organization could be, for example, I will not fire these commands, but let's log in into a registry. And that could be container registry mycompany.com. So it will ask me for a username, my user, and my pass. I will try to connect to this cr.mycompany.com DNS. Okay, it fails because it doesn't exist. I just invented that. But let's assume I'm successfully authenticated. From that point on, I can push and pull images to this registry with this DNS name. And now I need to adjust the tag to actually be able to push my image. So I will use Docker tag, and I will apply a tag that is suitable for me. So I used CND 103. That's the image that I want to re-tag. Then I provide the new tag. It says mycompany.com, company.com, library, whatever directory structure your registry will provide. And then I say container network display. Here I will use a full name because I'm not the only one that is dealing with this registry, and other people should identify what's the context of this Docker image just by looking at the name. That would be a great idea. So we will re-tag that, and let's look at the images list now. We can see we've created a new entry, but it references to the same image ID. So tagging is just adding another tag, another label to an existing image. It doesn't create a new image, it's just a logical tag. And with that done, I can actually say docker push. And here I will need to specify the complete name, because from that name it will deduct to which registry to talk to. And if I was logged in, I could actually push my container image now, and others could pull and use it. Excellent. Now we know how to work with containers from a Docker perspective. Let's head over to Kubernetes. And the first thing that we will learn is a very easy one, how to shorten the way we write Kubernetes, because we can just delete the 8 letters in the middle of the word and write Kubernetes as K8s. We will still speak about Kubernetes, or not K8s, whatever you would pronounce it. Just say Kubernetes and write it like that. In order to acknowledge what Kubernetes can solve for us, let's look at a world where no orchestration is able to take place, where we deploy our Docker runtimes within virtual machines and where we create our containers within these virtual machines. So this set of containers is our virtual shop, or not our virtual shop, our very, very real shop where we'll sell smoothies to our customers. So this is our stream of revenues. And because that's our only stream of revenues, we will make sure that this web shop is highly available. We will create a load balancer, directing requests from our customers into our 3 virtual machines running Docker and running the same set of containers within. Life is good. Our customers' relationship is great. And then an influencer nips on one of our smoothies and the requests and the count and the load explodes. And we need to react very quickly. So we create additional virtual machines. We install the Docker runtime in them, and we will adjust our load balancer to load balance the traffic into each of those nodes. So this is manageable. It's not pretty, but it's okay to deal with that if that's the only workload that we manage in our operations. And what happens if we release the second version of our webshop with social media integration or whatever? So now we need to log on into each of these virtual machines. We need to ramp down or delete the old version. We need to load the new version, the new containers. We need to make sure that we do not forget any of those Docker hosts, because then the load balancer would route traffic to an old version, and that is a completely new set of issues that we have to deal with on the help desk side. Kubernetes is able to help us deploying and managing applications across hosts. It will orchestrate our containers. And if we go in a 10,000 feet view above Kubernetes, we only see two components. And now that's pretty easy. So Kubernetes isn't so hard, right? We've got two components, the control plane and the workers. The control plane is the component that we will be working with as a user, as a developer, as an admin. And the control plane contains most of the processes that will orchestrate our workloads. What does that mean? There's a cluster state containing all the objects within the cluster, the Kubernetes objects. And there is a desired state that we want to achieve, but there might be an actual state that differentiates, that is different from the desired state. For example, I want to make sure that my web shop runs with 3 replicas. That is the desired state. The actual state might be one of my worker nodes, which is running our pods, exploded or just broke down, and some of these containers are currently not running. So the desired state and the actual state is different, and the control plane hosts a set of services, components, utilities, controllers that work constantly towards achieving the desired state of my cluster objects. So these two components is, as an overview, it's pretty common to run these components on a developer machine, on my laptop, within one virtual machine. For example, if you're using Docker Desktop, you can check an option in the dashboard, please start Kubernetes cluster for me. Then the exact thing happens. One virtual machine providing you with a Kubernetes, which from a technical standpoint is exactly the same than a big scaled up cluster on AWS. You can work with it, you can learn with it, you can see how containers are handled within Kubernetes. So this is pretty common. In production, we will separate these two areas of responsibility, and in fact, we will make sure as responsible operators that your control plane is highly available with at least 3 nodes. Why 3? We'll come back to that later. The workers are running our pods, so we will scale the number of workers according to our needs. Those workers could have individual hardwares supplied with them, for example, GPUs or a special set of APIC, and we can target our workloads towards specific workers. If you look at this cluster in more detail, we can see that we can provide access to the cluster, to the control plane, via a role-based access control. That means we are establishing certain roles with a set of permissions and assign users and groups to these roles. We can, for example, create a role that has access to our cluster as a whole. So we can have a resource pool containing all CPU, memory, IOPS from the whole cluster. Or we can create tiny slices. We can create namespaces where only a subset of groups have access to. This is a logical separation of resources, mainly for the use to avoid name clashes. For example, we can run a pod with a given name in namespace A and another pod with the same name in namespace B without them interfering with each other. That is especially useful if we have departments or projects or whatever, people that can use the same cluster resources without the need for them to really talk to each other about naming conventions. The namespace here is a Kubernetes object. And it's the first object that we learn about. A namespace is possibly a measure to separate workloads from each other. Like if I have a pod running in A, I have another user group, he cannot access this pod and interact with it. But still, if I think, would it be a good option to run and host business critical workloads in namespace A, and very developer-friendly, open namespace C, where everyone can do everything and access is a little loose? Probably not. I would separate these workloads in different clusters and not only in different namespaces. The one who listens very closely to my words would say, hey, we are talking about containers and now you use the word pod. What is that? Pod is the smallest workload unit within a Kubernetes cluster. A pod is not a container because a pod contains another container. Always. A pause container is stored alongside the actual application container, and the responsibility of that is just to hold the network namespace open, no matter what with our application container might happen or not. Additionally, we can run two application containers when they have a very tight coupling with each other together in one pod. Or we can use something like an init container that downloads certain data from a GitHub repository, for example, and stores that in a volume that is a shareable storage area that all containers within one pod can access. After this init container successfully quits, the actual application container, the web server, is started and it can start serving the content found on the volume. That's a pretty common mechanism to use init containers for. This totally combined, like multiple containers, volumes, and the pause container, is called a pod. Again, the right-hand side is totally optional, and Kubernetes actually suggests that if you do not necessarily have to differ from one container within one pod, you shouldn't. Normally this is enough, and normally instead you would create two pods, each hosting one container if they need to talk to each other. So, being 90% honest, you could say a container is a pod. Semantically, of course, is incorrect. But if that helps you inside your head for the moment, that's perfectly fine. Now let's look how we tell the Kubernetes cluster, I want to start a pod. We've got the first component that we learn about is the kube API server, and as I said before, the control plane is responsible for taking our request and executing the commands that we issue against it. So we as people or automated processes talk to this HTTP REST API. The control plane will validate the request and store the resulting cluster state in a database. This is not a relational database with tables relating to each other, and it's very complicated and perhaps a bit slow. No, it's a key value store. So very, very simple. A key, a value, a key, a value, a key, a value, but super fast. And why do we need 3 control plane nodes in order to achieve high availability of our control plane? Because etcd requires at least 3 peers to function and to make sure that the data is synced and available. And it's a very common pattern to run the etcd database on each control plane node. Of course, we can take this etcd cluster and separate it from the Kubernetes cluster and run it separately. But this pattern is not so bad and found in the wild very commonly. Because the data inside and the kube API server in combination are forming the heart and soul of every Kubernetes cluster, we should take a backup to restore cluster state if disaster strikes. And how are we actually interacting with the Kube API server? We as persons might not be able to send and form HTTP requests, so we will be using kube control, for example. That's the command line utility from the Kubernetes universe, and it's pretty awesome, pretty easy to understand, and pretty mighty. Automated processes, one of the drivers of Kubernetes success story, are, for example, CI/CD pipelines. Just in short, CI/CD stands for continuous integration and continuous deployment. I will continuously integrate the changes my developing team forms and transfer them after they are tested automatically for correctness and if they are breaking existing stuff, and after being peer reviewed in a manual review process into a next release of our software. This is continuous integration. Once this is done, the next step, continuous deployment, is kicking into action. And this source code is packaged as a container using a suitable build step, and the resulting container is uploaded into our registry and then pushed into our Kubernetes cluster for execution and for running in production. So the time from merging a change in source code till we see that change in production is getting shorter and shorter. I, as an administrator or operator, will use kube control or other suitable tools to interact with the cluster. And with that said, let's look a bit more in detail about cluster state. The Kube API server and its etcd database are the core of every Kubernetes cluster. And I will provide the cluster with Kubernetes objects that I want to run, that I want to create, that I want to edit or update or delete. And for creating, for example, a namespace or a pod, I will create an object with metadata and a spec. Metadata, for example, includes the name of the object, the name of the namespace, the name of the pod. The spec describes the objects completely. So we can see on the website of kubernetes.io there's an API reference clearly describing the spec of each object, a namespace, a pod, a replica set, a service, an ingressing resource. Everything a Kubernetes server knows about is described in detail. There are optional parts, there are required parts, and the spec needs to follow this in combination with the Kubernetes version. We send that over to the Kube API server where it is stored in etcd, and it's additionally creating a new field in this object, the status. And this is done for every object that we create or update. And the status is constantly updated from other components running in the cluster. So the Kube API server knows about the status of every object within the cluster all the time. And this is in total creating a desired and an actual cluster state. And Kubernetes as a platform is constantly trying to move from the actual state into the direction of the desired state. Let's take a quick detour about how we can actually talk to Kubernetes, because we have two ways to command it: imperative commands and declarative commands. You all know about imperative commands because that's how we normally work with systems. We open a command line and say, create a namespace, create a pod, create a replica set, create a directory. We open an editor and make a change in a config file, save it, and apply this config. This is all imperative commands. When we lose our cluster and we want to again achieve this, a one namespace and a pod with 6 replicas in total, we would need to execute these same commands in the exact same order to achieve the same end result. So these are really commands to this, then that, and we need to document that. And of course, we are super great at documentation. Every operator around the world would agree on that. The declarative approach is a little bit different. Now let's assume we have a namespace and 3 pods running in there. And we just say to the system, please deploy a pod with 6 replicas in the namespace. And you can omit the please if you're really rude. The system will then check, okay, I've got a namespace already. I know about the pod, but the replicas? Now we are golden. So in contrast to the commands, we describe the desired outcome, but we will not list the commands really necessary to achieve it. That is the responsibility of the system in itself. And the great thing about this is that we can create a description in a text file, and we can put this text file into our GitHub. And we have a version of changes in time, what happened with our cluster, who authored the change, and why, because he might have documented the pull requests on the version when creating version 4 of our description, for example. We can always go back in time if we want that. And that's a super nice thing to have, because now we have got the second file in textual form forming our cluster. We've already got the Docker file describing how we create a container. Now we have a description of how this container should run on our Kubernetes cluster. Can you see the places falling into the puzzle pieces falling into places when we're talking about an automated CI/CD process? Let's transfer these 2 imperative declarative commands into kube control commands. On the one hand, we have create, remove, replace. On the other hand, we have kube control apply. And while create, remove, replace are perfectly fine to use on the command line, apply always requires a file that is read and executed. Do we think that imperative commands are obsolete? Of course not. For example, our web shop serves the traffic to our customers with 6 replicas really fine, and the next influencer might advertise willingly or unwillingly our smoothies. Now we know that over a short time frame, the amount of requests will ramp up, but then it will get back to normal rather quickly. In that case, it's not really necessary to hold the information, please ramp up to 10 replicas, and put that into version control. I would then issue an imperative command, scale up to 10, and after 4 days, I would say scale down to 6 again. So always combine the 2 ways to work with a Kubernetes cluster and decide which command is really the best one to use. Let's run a pod. You can see on the right top side, the worker nodes are currently empty, no containers running. We issue kube control create pod, CND, that's the name, and we specify the container image to load and run. But we want to look at how declarative works. So we say apply -f file, load the file cnd.yaml, and execute. YAML stands for yet another markup language, and it's very easy to read as a human and as a computer. It has key value pairs separated by colons, and it has indentation grouping several of these key value pairs into groups. It has even lists, which we'll learn about in a second. So first, we tell the system what kind of object are we dealing with. Here it is of kind pod, because we want to create a pod. That makes perfect sense. The API version is something that I already explained to you, because the pod spec is targeted at a specific Kubernetes version. And because Kubernetes is a very lively ecosystem, the way we describe a pod within a spec might change in the future. So this API version v1 is valid for Kubernetes version 1.24. Potentially this might change. For example, in Kubernetes version 1.25, the description, the spec changes and is described in the API reference under the namespace rps/v1. And on the same time, the documentation that is currently current will be marked as deprecated, and we will be given a time span when a description of a pod with a v1 AP version is no longer accepted by Kubernetes in this case, when Kubernetes version reaches 1.32. So we always need to look out for this API descriptions, and we need to adapt our YAML files accordingly. But let's go back to the YAML itself. We learned that a Kubernetes object has metadata and spec, and this YAML file reflects that knowledge. We've got metadata. We got a name, CND, and we got labels over here. Labels are a great instrument in Kubernetes because it allows us to select and group objects. We will do that later on. Here we define custom user-defined entries, and indeed there is no spec that says a label must be of type. This type.info, we as an operator, as an admin, as a developer invented or said we need type info. We need app container network display. So key and value is user defined. Annotations are a little bit different from that. Annotations are for example, operators that might be installed in our Kubernetes cluster. Perhaps we even created and programmed an operator by ourselves that talks to other components, and it will watch for annotations of a specific key value. And if it finds these, for example, my-operator discard, something will happen automatically for us. But this is not Kubernetes core specific. It is specific for components that we install additionally into our cluster. And the documentation of these components will provide us with the annotations we need to add to this metadata field. The last part is the spec. I said that multiple times already. It's the description of the pod, and it is described in the AP reference. At the very least, we need to provide a containers key, which is a list of containers to start when the pod is created. We remember, we might have multiple application containers, or we could add init containers with a list of containers to start before the actual application container is running. Here we only have one container. Its name is network container display. The image that we run is specified. We even put a resource limitation on here. You only have 128 megabytes of RAM. This is a C group, a control group for the Linux kernel when this container's environment is prepared. And of course we do have, like in the Docker file, the container has a process that listens for incoming requests on port 3000. When we execute that, and after a smashing animation later, we do have our lonely pod populating the first node in our worker. And now let's see what is actually happening behind the scenes when we issue this command. Let's create a pod, but this time from the perspective of the Kubernetes cluster. So we issue this command through the HTTPS interface to the Kube API server, and then it is validated. Who are you? Are you allowed to do that? And is the request according to a spec that I understand, given my Kubernetes version of 1.24? If all these are checked and said, okay, done, that matches my expectations, the cluster state is updated within the etcd database. And the user gets the signal, all right, we will do that. The next component that will kick into action also lives on the control plane. It's the Kube scheduler. The Kube scheduler is responsible to schedule workloads to the worker nodes. And it sees in the cluster state that we should run a pod, but we have not yet determined where. So it will look at all the worker nodes and it will compare, for example, the resource requirements of this pod to the free resources or available resources on each worker node, or there's something like pod affinity and pod anti-affinity. Should this new pod run, or should it absolutely not run with another pod on a worker node? And this initial process eliminates certain worker nodes from the next step, a ranking of the remaining worker nodes. From 1 to 10, each one gets a ranking. The one with a high score wins, and in this case, worker node B is the designated worker to run this workload at. The Kube API server will be updating the cluster state again, and now the worker B will see, okay, wait a second. I'm worker B, and the kubelet component will monitor the cluster state too. The kubelet is a process that runs on every worker node, and it will see I need to start a pod. Alongside the kube proxy, one of the other components running on each worker node, it will create a certain set of config. For example, an IP address will be generated by the container network running on the complete cluster. We will adjust IP tables or IPVS to actually make this IP address known on other worker nodes, and we will create an DNS entry within our Kubernetes internal DNS service. And together with the container network, this is all done, and the container runtime also installed on the worker node will finally run our pod, and the desired cluster state and the actual cluster state matches. Everything is great. The third component will come into play when something happens. This is the kube controller, and it's actually a set of controllers living in the same binary. For example, there is a node controller, and when a worker node fails to update its state, like how am I alive, what are my pods running at, and how many resources do they consume, this information is constantly passed to the Kube API server. And when this information is failing to arrive, after 5 seconds, the node controller would say, wait a second, something is wrong. 5 seconds is like so super long, and nothing heard from worker B. Let's watch it for another 55 seconds. And if after 60 seconds in total, the worker fails to update its health status to the Kube API server, the node controller will update the cluster state and say, the pods is no longer scheduled. What will happen then? Well, of course, the kube scheduler will be notified or will see the cluster state and the cluster desired state. They are not matching any longer because the pod is not assigned to a worker, and this whole process will start again. What you learn from this slide is there are plenty of components residing on the control plane and the worker, all with the same goal to achieve the desired state or to retain it. And this is a complex, ongoing process of communication of messages, all targeted to the Kube API server as a core and central component. Let's look at another Kubernetes object, deployments. We learned that a pod is the tiniest way to manage a workload. Deployments are way up higher in the Kubernetes object hierarchy. It is responsible to deploy containerist applications in the way we want to have it in our first example with Docker hosts and Docker containers running on different Docker hosts. So we want to manage a deployment, a version of our application of our Smoothie web shop. For example, we just want to say I need 6 replicas of my Smoothie web shop. And on the top right corner, we already see that 3 pods are already running. That's perhaps the pod that we started with the first YAML that we learned about. And then we dove deeper into Kubernetes and learned about deployments and saw the benefits, and now we want to reap them. So let's look at the YAML file. It looks way more complicated than before, at least a little bit longer. But if we look very closely, we can see that the bottom part, the template within the deployment spec, is the exact same spec as in the kind:pod before. All that is missing is the API version and kind:pod, and then it's exactly the same. So we can skip that part and suddenly it's not so intimidating. Let's start from the top. We are talking about a deployment here. The spec is described in the API version apps/v1. The metadata is not so interesting for us, so we dive directly into the spec here. There is a selector which matches certain labels on our pods. That is something that I mentioned before. Labels are a great way to group objects or to do selections. And this is what's happening within a deployment. We already have started 3 pods. And these pods have a label with a name app and a value container network display. So these 3 pods would be selected when the deployment is created. We do have the statement we want 6 replicas. And with the given knowledge now that 3 are already running, we know the deployment will probably create 3 additional ones, resulting in 6. And this is because of the label selector. We've got an additional information about how we will be dealing with updates. So for example, the next version of our web shop, we will look at that in a second. Again, the template is just a pod specification. And whenever the underlying replica set object that will be created with a deployment sees that a new replica needs to be created, either because the number of replicas is changing or a pod is failing or crashing and needs restarting, this template will be used to instantiate this pod. It will not look at the pods that are already running and try to figure out what pod spec is probably based on that and take that. No, it needs this template. And when we execute that, we can see what happens. I already spoiled that. So 3 new pod instances will be created, forming a replica set of 6. And this part of the deployment object is fulfilled. The deployment object has a function to deal with updates or rolling back an update which failed for whatever reason. And this is something that we can watch now. We defined rolling update max search 3. That means when you need to do an update, you do not have to stick with 6 instances of this pod or 3 replicas, 6 replicas. You can create 3 additional ones to smoothen the update process a little bit further. So when we execute it now, for example, we updated the image version to 1.1.0, what will happen? It will create 3 pods with the new version, replace 3 old ones with a new version, and then kill the remaining 6 old version pods, resulting in 6 replicas of the new version. Pretty smooth. We will not forget to update one version on one of our worker nodes because Kubernetes will deal with that. That's pretty nifty. And our last dive will be into pod communication. This is a pretty complicated topic, so this is the last bit of attention that I will need from you for today. Let's assume we have 3 worker nodes and 2 deployments. Our smoothie web shop is now consisting of 3 web servers facing the customer and, for example, a highly available database in the backend. So we got a web server deployment, 3 replicas, and a database deployment, 2 replicas. The container network will pick an IP address for each of these pods. That's a requirement from Kubernetes networking. Each pod gets its own IP address. And the address space this IP address is taken from is defined when creating the cluster. This is the pod network IP address range. This is a private IP address range only known within the cluster. And when one web server wants to talk to a database within one worker node, we need to make sure that they are indeed able to talk to each other. The IP address is only sitting in the namespace of the pod. So how is it done? The container network implementation will create a virtual bridge on the worker node and will create 2 virtual Ethernet cables, tossing them into the namespace of the pods and thus connecting them creating an overlay network on the actual physical hardware. Here, within one worker node. So we're not talking about network interface cards of the worker itself. This is done when we see how does a pod talks to another pod, but across worker nodes. Again, the overlay network will create all virtual bridges and virtual Ethernet cables to construct a network spanning all worker nodes, enabling all pods to communicate with each other without the need of network address translation. So no NAT is happening here. It's all direct IP config and all direct IP communication, and therefore a pretty easy to grasp concept. If I say pretty easy, how does the web server know about the IP address of the database? And even further, this is a replica set, so we want to have 2 replicas of the database. What happens if this pod crashes and needs to be restarted? It will come up with a completely new IP address. So are the web servers somehow be configured to listen for IP address changes? No. Alongside the replica set, which is responsible to keep the amount of configured replicas running for this deployment, there's another service generated. And this service is known to each of the worker nodes. It has an IP address from another IP address range, so it's another private IP address range, this time the service IP address range, again specified when creating the cluster. It has configured endpoints, and these endpoints are the IP addresses of the database when we are talking about the database service. If a pod is destroyed and the replica controller sees I need to restart one of those databases and the new IP address is configured, this endpoint is updated because again it is selected by labels. Pretty nifty. Still, we do not know about IP addresses, but we have core DNS, the DNS component running in our cluster, and now the web server can use this DNS name to target the service by saying database.svc for service.cluster.local. This is naming convention. And with that, communication is established, for example, in a round-robin way. So no matter what database backend we are targeting, just give me the data set that I need to provide my customer with his user interface. This is pretty awesome. So communication within the cluster is very, very nice. It's very easy for us as a developer to create a web server, to use a database. Life is very, very great. But those ranges are all private IP address ranges. How can we make sure that the customer's actually buying something from us and we get our salaries at the end of the month? On public clouds, AWS, Google, Azure, you name it, there is a service of type load balancer that we can deploy, which will create a public IP address for us and takes certain measures to direct the request from the users into our cluster, where again it will be just routed according to our network interfaces or our service or container network. But on-premise clusters do not have these by default. So this is just a public cloud offering. Fortunately, there are several components, open source components and closed source components that we can additionally install into our cluster. One of them is MetalLB. It has a super nice name and it has super nice functionality because here we can reserve an IP address range from a public IP address range dedicated to MetalLB, and whenever I create a service type load balancer, it will pick one of those IP addresses and it will pick one of the worker nodes in my cluster and attach this public IP address to the actual network interface card on the host. Then it will employ known routing protocols like ARP or BGP to direct traffic towards this network interface card. It basically says, if you have traffic for me, please route it here. I'm at home here. And that brings the requests into our cluster where they are processed further. Wow, now we covered a lot of ground. Let's conclude the session with answering the 3 questions we started with. What is Kubernetes? Kubernetes is a flexible automated platform. You saw how many components are working for you to achieve your goal, to achieve this desired cluster state. You run your containerized workloads in a secure manner. What does it mean? First, we got role-based access control. So we actually define who has which permissions to interact with the cluster. But also, our services can be defined really securely in a way, like from an operator standpoint. We do have multiple replicas, and if our containerized applications can deal with this paradigm, it's a great match. But on the other hand, it's very complex. All these little tiny cogwheels whirring around and working together, it's not the simplest of technologies. And how does it work? I hope I gave you a good enough introduction to place mental pins into your brains, to know about what is a container network, what's the repository, what are the Kubernetes control nodes, components, and what lives on a worker node, and how do they interact. And if not, I hope I sparked your drive to learn more about how Kubernetes works, because it's really a great tech to understand, and it's really something that takes all your knowledge to the next level. Now, do I need it? Well, the answer, as always, is it depends. Kubernetes is just a technology. If you do not have a problem that is solved by Kubernetes, then you probably don't need Kubernetes. If you're not dealing with, for example, frequent updates of containerized applications and do have processes in place that builds a pipeline that pushes your releases into the public and into your customers, if that's not your use case, you really ought to know, is it the right tech for me? Not because everyone talks about Kubernetes, it does not imply that you need to do Kubernetes as well. But it has automation as a core functionality, and it's super open by design. So it's not like here is instructions on how Kubernetes is installed. Even that is missing, but you will see there are different options presented to you in the documentation, and you choose the best way for you and your institution into your org. Open architecture goes as well into the technical details of Kubernetes. I always talked about a container network, but what I hid from you so far is that there are a myriad of options. What kind of network do I actually need? In my home lab, I use Flannel, very easy overlay network based on VXVLANs. But you can employ Calico, for example, way more complicated, but way more features, but requires BGP. My home lab doesn't have that, so could not employ it. I can use VMware NSX or Cisco ACI software-defined network solutions, not only targeting to Kubernetes, but to my whole data center. What I want to imply is, in order to select the correct solution, you need to know the differentiators between them, and you need to have a broad knowledge about, for example, networks. You need to choose your storage provider, because it's the same exact thing. How is storage provisioned into my Kubernetes cluster or into my pods? And that brings me to the next question. How do you want to service Kubernetes? Or if you provide some kind of container service or Kubernetes service for your organization, how would you design it? What is your service level here? One thing that you always hear is you build it, you run it. And there's a truth in that words, because you have mainly two ways to approach Kubernetes as a service. You can either say, I define how I run my Kubernetes control plane and worker nodes, and you can give me your containerized applications and I run it for you. That means you have a very strict defined way of running Kubernetes, and that might not match all requirements from your developers, which for example need specific container network solutions because they want to have a service mesh discovery. Or you can say, I only manage the control plane and I will update Kubernetes versions as they are released in a defined release cycle. That means that you will give your developers a Kubernetes cluster where they will install their network of choice or the ingress resources of choice or the load balance of choice, and they are responsible to keep that in sync with the Kubernetes version alongside with you, so you will be working together. You see, Kubernetes is not just a setup exe and it runs installation besides Docker Desktop and this checkbox in the dashboard, but that's not production, right? So I want to end this lecture, this session, with a cheesy quote from Kelsey Hightower. You give a man a container and he will be busy one day, but if you show him Kubernetes, he won't do anything else his entire life. But it's pretty awesome, it's interesting text, so it's not the baddest. So thank you for your time, thank you for watching till the end. If you have questions, please reach out. I hope to hear from you and get in touch. Bye bye.